There's a part of us that thinks we've already figured out the sun. We learn about it early on, hot, bright, 93 million miles away, been burning for billions of years. It feels stable, predictable, almost boring, but that's not really true anymore. Right now, the sun is hitting the most active point it's been in over a decade. And it's not just sending off flares and storms, it's doing things we didn't think it could do. One NASA probe flew right through the chaos and saw something strange, something we've never caught in action before. This wasn't just another solar flare. Multiple eruptions slammed into each other, fused together, and created a magnetic ripple so powerful it bent part of the sun's outer layer. Scientists are still trying to figure out what that means. And here's the part that's bothering a lot of them. This kind of behavior doesn't really fit the models. It's not supposed to happen like this. So, now we're left with a question we haven't had to ask in a long time. Do we actually understand how our own star works? Or has it been hiding something in plain sight? You probably haven't noticed anything unusual when you look up during the day. The sun still rises and sets like clockwork. No changes to the color, no warning signs in the sky, but behind that calm appearance, something big is happening. We're right in the middle of something called solar maximum. It's the most active phase in the sun's natural cycle, a period when the magnetic field gets tangled, twisted, and unstable. And when that happens, the surface becomes restless. Sunspots form, flares erupt, and huge clouds of charged particles get hurled into space at high speeds. This cycle has been going on for billions of years. It repeats roughly every 11 years, like the sun breathing in and out. One cycle ends, the next begins. And each time, the magnetic poles flip, north becomes south, and vice versa. It's not instant and it's not clean. The flip takes time, and during that period, the sun becomes chaotic. Right now, in 2025, we're at the peak of solar cycle 25. That means the magnetic field is tangled up more than usual. The number of sunspots is going up, and those sunspots, they're not just dark patches. They're active regions that store enormous amounts of magnetic energy. Think of them like pressure points on the surface. When the pressure builds too much, something snaps and you get an explosion, a solar flare, or worse, a coronal mass ejection. Solar cycle 25 wasn't expected to be this strong. When it started in late 2019, predictions said it would be weaker than the last one. Quiet, mostly uneventful. But that's not what's happening. Over the past few months, scientists have been seeing more sunspots than they expected. And they're not evenly spread out either. Some of them are forming in clusters, erupting one after the other, almost like a chain reaction. That's where things start to get interesting. Because every time one of those flares or coronal mass ejection bursts off the sun, it sends radiation and charged particles out into space. Most of the time, that energy just keeps going. But if the direction is right, if it's aimed at Earth, it can mess with satellites, interrupt radio signals, and even damage power grids. And this isn't theoretical. We've already seen real effects from this cycle. In May 2024, a series of powerful solar storms from active region AR3664 caused significant GPS disruptions in high-latitude regions like parts of Canada and Scandinavia due to ionospheric disturbances. These storms also triggered strong radio blackouts, impacting shortwave communications critical for airlines over the North Atlantic. While no injuries occurred, these disruptions required communication workarounds and raised serious questions about our preparedness for stronger solar events. Now, in mid-2025, we're at the height of the storm. The peak of solar maximum isn't a single day. It's more like a messy season that lasts a year or two. That's why this summer is getting so much attention. Multiple agencies, including NASA, NOAA, and ESA, have started issuing more frequent space weather alerts. And amateur astronomers, they're spotting auroras in places where they're rare, such as Arizona, France, and even as far south as parts of the Mediterranean region. But even with all this happening, the general public barely hears about it. Unless it causes an outage or cancels a flight, space weather doesn't make the news. It's quiet, invisible, easy to ignore. And that's part of the problem. Because while everything seems fine on the surface, the sun is pushing out more energy, more flares, and more magnetically charged debris than it has in over a decade. It's like living next to a volcano that's suddenly more active. And most people don't even know it's rumbling. This isn't fear-mongering, this is physics. And now that the sun is fully awake, scientists are watching closely. Because if anything unusual is going to happen, something that challenges the models, it's going to happen now. Before we continue, if you've ever landed in a new country and immediately gone into panic mode because there's no Wi-Fi, you'll know how frustrating that feels. Either you're stuck paying insane roaming fees, wasting time hunting for a local SIM, or taking your chances with someone selling one outside the airport. I've been there, and it's the worst way to start a trip. That's why I use Saily. It's an eSIM app, which means no physical SIM card, no switching tiny trays in your phone, and no standing in line just to get connected. You install it once on your phone, pick a plan for wherever you're going. They've got coverage in over 200 destinations. And the second your plane lands, you're online. It even has built-in privacy tools that block ads, help you save data, and keep your browsing secure. It's genuinely that simple. Open the app, choose your destination, and use code FEXEL or scan the QR code on screen, and you'll instantly get 15% off your plan, making it easier to stay connected without dealing with extra costs when you return home. If we had tried to do this 20 years ago, it wouldn't have worked. The heat, the radiation, the distance, it would have melted the instruments before they even got close. But today, we've built something that can survive there. It's called the Parker Solar Probe, and it's not just watching the sun from a distance, it's flying right through its outer atmosphere. That alone is wild. Most space missions keep their distance from anything dangerous. Not Parker. It's the first spacecraft designed to dive directly into the corona, that faint outer layer of the sun that we usually only see during a total eclipse, reaching speeds of up to 690,000 kilometers per hour to swiftly navigate this extreme environment. To survive that kind of heat, the probe is equipped with a special carbon composite heat shield that can withstand temperatures over 1,300 degrees Celsius, while keeping the instruments inside just above room temperature. Since its launch in 2018, Parker has been getting closer and closer with every orbit. By late 2024, it reached a point where it was skimming just 7.3 million kilometers above the surface. That sounds like a lot until you remember the sun is massive. Over 1 million Earths could fit inside it. At that altitude, Parker was literally flying through solar eruptions as they were happening. And then something strange happened. During one of its most recent flybys, Parker passed through an active region where multiple CMEs had just erupted. Normally, these coronal mass ejections burst outward like separate explosions, independent events. But this time, something was different. As Parker approached, it picked up signs of an ongoing collision, not just between plasma clouds, but between their magnetic fields. One CME caught up with another, and the two started merging. That alone is unusual. What's weirder is what came next. Instead of just combining into a larger storm, the merged structure began to compress and warp the surrounding magnetic field in a way that hadn't been modeled before. The magnetic loops above the sun's surface, normally smooth and arched, began to twist downward like tangled rope. One part of the corona folded in on itself. It was like watching waves crash together, but made of superheated gas and magnetism. Parker flew right through it. The instruments on board recorded a sudden spike in particle density, a drop in local magnetic pressure, and a brief burst of radio signals that didn't match any known signature. For a few minutes, the data looked like static, until it didn't. When scientists decoded it, they realized Parker had flown through a high-energy shock front, created not by one flare, but by the fusion of two. It's being called a compound CME, And while these kinds of events have been theorized, we've never had direct close-up measurements from inside one, until now. And it raises questions that go beyond just solar physics. Because when these things happen, they don't stay in the corona. They shoot out into the solar system, carrying magnetic structures that interact with everything they touch. Satellites, astronauts, Earth's magnetic field. So now scientists are going back over years of data, trying to figure out how many times something like this might have happened without us knowing. Did we miss earlier compound CMEs just because we weren't close enough? Did past blackouts or anomalies line up with events like this? The answers aren't all in yet. But this one encounter, just a few minutes of data from a tiny probe buried in solar plasma, could change how we understand the way energy moves through space. Not just in our system, but in other stars too. And it's all because Parker went where nothing else ever dared to go. When the sun fires off a CME, it launches billions of tons of charged particles across space. If that cloud hits Earth, it slams into our planet's magnetic field at incredible speed. Most of the time, our atmosphere and magnetic shield deflect it. But not always. Sometimes the incoming energy is strong enough to compress our magnetic field. That's when things start to go wrong. Satellites get overwhelmed by radiation and either shut down or start behaving unpredictably. High-frequency radio waves, used for everything from aircraft communication to emergency services, can vanish for hours. GPS becomes unreliable. And in extreme cases, the surge can cause voltage spikes that trip power grids. Historically, we've seen the devastating effects of solar storms. In March 1989, a geomagnetic storm triggered by a CME led to a massive blackout in Quebec, leaving 6 million people without power for up to 9 hours. And in 2003, the Halloween storms caused transformer damage in Sweden and South Africa while disrupting satellite operations and radio communications globally. Those storms weren't even the strongest on record. That title goes to the Carrington event in 1859. Telegraph wires burst into flames. Operators got shocked by their own equipment. Auroras were visible as far south as the Caribbean. If that happened today, with our global reliance on satellites and digital infrastructure, we wouldn't be talking about pretty lights in the sky. We'd be dealing with weeks of outages, financial chaos, and transportation gridlock. And here's where things get real. The kind of event Parker just observed, the merging CMEs, the shock fronts, the compressed magnetic structures, that's the sort of thing that can amplify the effect when it hits us. One CME is bad. 2 hitting back-to-back, that's worse. But when 2 merge and arrive as a single, dense front, it can overwhelm even the best shielding systems we've built. That's what made scientists sit up after this latest Parker flyby. Not just because it was cool, because it was a warning. In late May 2025, NOAA detected a complex CME system approaching Earth, which evolved into a significant geomagnetic storm by early June. It wasn't predicted to be that strong and arrived faster than expected due to its high speed. It caused intermittent satellite issues, disrupted GPS signals in regions like the Pacific, and triggered low-latitude auroras as far south as southern Europe and parts of North Africa. People saw it as a light show. The scientists watching Parker's data didn't. They recognized how these storms can intensify before reaching Earth. And next time, it might not just be a colorful sky. That's the whole point of missions like Parker. Not to chase beauty, but to buy us time. By understanding how these storms form, combine, and signal their approach, we can build better systems to mitigate their impacts. Because the sun doesn't care about our satellites or our airline schedules or whether we've finished building shielding on some new spacecraft. It just moves through its cycles. And sometimes, those cycles hit harder than expected. We're lucky this time. But luck isn't a long-term plan. It's strange how something so dangerous can also be beautiful. You've probably seen the photos, green and purple lights twisting across the night sky like curtains in the wind. That's what a lot of people think space weather looks like. They don't see the side of it that knocks out power stations or fries satellite electronics. They see the auroras, and it all feels kind of magical. And yeah, the lights really are incredible. They happen when high-energy particles from the sun crash into Earth's magnetic field and get funneled toward the poles. As they interact with gases in our upper atmosphere, oxygen, nitrogen, they produce those glowing waves of color. Usually this happens far north or far south, near the magnetic poles, places like Iceland, Canada, or Antarctica. But lately, something unusual has been happening. During the past few solar storms, those auroras have started showing up in places that don't normally get them. States like New Mexico, cities like Rome, islands in the Mediterranean. Not just once, multiple times this year. And every time that happens, people take photos, post them online, and talk about how rare and beautiful it was. But no one really asks why it happened, or what else was going on at the time. Because for the aurora to reach those latitudes, something has to push Earth's magnetic field out of alignment. A solar storm has to hit hard enough to flatten the field, opening pathways for particles to reach parts of the atmosphere that are usually out of range. And when that happens, it's not just light shows that follow, it's communication dropouts, navigation errors, and power fluctuations. During one of the recent storms in early July 2025, a regional power operator in Chile reported brief voltage instability across its southern grid. Nothing dramatic, just a flicker. But it happened right as a surge of solar wind was hitting Earth. At the same time, several satellites in low Earth orbit had to switch to safe mode due to unexpected radiation spikes. All of that came with the auroras. Same event. That's the part people forget. The pretty lights and the outages are two sides of the same coin, and as solar activity ramps up, both are going to become more common. It's not all bad. There's a real opportunity here too. With this increase in activity, scientists are getting more real-time data than ever before. Every flare, every CME, every aurora, it's all being tracked, analyzed, and used to improve space weather forecasting. That's huge. A decade ago, space weather alerts were vague and often late. Now we're getting better at predicting when storms will hit, how strong they'll be, and which systems are most at risk. That kind of forecasting could save satellites, prevent blackouts, and even protect astronauts during future deep space missions. But we're still playing catch-up. A lot of infrastructure, especially older satellites and terrestrial power systems, just weren't designed to handle the kind of solar behavior we're starting to see. They weren't built for multiple CMEs merging in mid-flight, or for coronal loops collapsing back into themselves, or for the kinds of bursts Parker is flying through right now. So, while the public sees a once-in-a-lifetime aurora, scientists are watching the same event and thinking, this could have been worse. That gap in awareness, that's something that has to close, because the sun isn't done, not even close. The Parker Solar Probe isn't the only one watching the sun up close. There are other eyes out there, each with its own vantage point, its own tools, and its own goals. Together, they're giving us something we've never had before. A coordinated, multi-angle view of the most unpredictable object in our solar system. Let's start with Solar Orbiter. It's a joint mission between the European Space Agency and NASA. While Parker is busy diving straight into the sun's outer atmosphere, Solar Orbiter takes a more distant route, giving it a broader view of the entire solar disk. The probe's orbit is tilted, which lets it observe regions that are almost impossible to see from Earth, like the sun's poles. And that matters a lot, because the magnetic field that controls the sun's activity is tied to those polar regions. They're where the field flips during each solar cycle. If you want to understand how that reversal works, how the field collapses and rebuilds itself, you need to watch the poles. In early 2025, Solar Orbiter captured the first ever detailed images of the sun's south pole. Not artistic interpretations, actual images. And what they showed was a region more chaotic than anyone expected. Twisted magnetic strands, fast-moving loops of plasma, and active zones that seemed to rotate independently of the surface below. Nobody was exactly sure what they were going to see, but this wasn't it. Models predicted a smoother structure, with relatively even magnetic behavior. Instead, what they found looked more like turbulence, layers of motion stacked on top of each other, out of sync. It raised a simple but important question. What's actually driving the sun's magnetic cycle? Because if the poles don't behave like the models said they should, maybe the cycle itself works differently than we thought. Then there's Muse, the multi-slit solar explorer, set to launch no earlier than 2027. Once operational, it will do something new, capturing high-resolution, multi-layered images of the solar atmosphere using extreme ultraviolet light. This will provide scientists with a kind of 3D scan of how energy moves from the sun's surface into the corona. MUSE is designed to observe small-scale changes that happen in seconds. It will track events like magnetic reconnection, sudden violent snaps where magnetic field lines break and reattach, releasing huge bursts of energy. These aren't always tied to big flares or CMEs. Some occur in quiet regions of the sun with almost no visible warning. Once operational, Muse is expected to show that these tiny events happen more often than previously thought, and their cumulative effect could be significant. That's important because it could help explain why the sun's outer atmosphere is so much hotter than its surface. For years, that's been a mystery. The corona can reach temperatures of over 1,000,000 degrees Celsius, while the surface is just under 6,000 degrees Celsius. That shouldn't happen. If small-scale energy bursts are constantly heating the corona from within, then Muse's observations could bring us closer to solving this long-standing puzzle. And finally, there's Punch, a group of small satellites working together to image the solar wind. Most of what we know about solar wind comes from direct sampling, like what Parker is doing. But Punch is visualizing it, capturing not just the outbursts, but the steady flow of particles the sun sends out every second of every day. Why does that matter? Because the solar wind is the background radiation of the entire solar system. It shapes planetary magnetospheres, drives comet tails, and affects how interstellar material moves past our sun. The more we understand it, the better we can track how disturbances from solar storms ripple outward and affect distant spacecraft, or even future missions to Mars. Each of these missions is doing something different, but together they're filling in the gaps. Parker gives us a close-up. Orbiter gives us the context. MUSE, set to launch no earlier than 2027, will reveal the mechanics of small-scale solar dynamics. Punch gives us the flow. And the deeper they look, the more it's becoming clear that the sun isn't as well behaved as we thought. It doesn't always follow the patterns we've been using for decades. And now that we're watching from every angle, we're starting to see just how much we've been missing. This is the part where things get uncomfortable. Not because the science is unclear, but because no one really wants to think about it. We've seen what the sun can do. Flares strong enough to blind satellites, coronal mass ejections that shut down power grids, solar storms that light up half the planet. And yet, all of that, everything we've experienced so far, might be small compared to what the sun is actually capable of. The idea of a superflare isn't science fiction. It's a real concept based on observations of other stars that are similar to our sun. Astronomers using space telescopes have seen stars just like ours. Same size, same temperature, same general behavior, suddenly erupt with flares hundreds or even thousands of times more powerful than anything we've recorded from our own star. These superflares release an enormous amount of energy in a very short time. Enough to not just disrupt electronics, but to physically damage spacecraft, destroy parts of Earth's ozone layer, or overwhelm even the most hardened power grids. The first time this idea came up, the thinking was simple. Those stars are younger, or faster spinning, or maybe just different. Basically, it couldn't happen here. Our sun was supposed to be more stable, but the more we study these other stars, the less solid that assumption becomes. Some of them look almost exactly like the sun. Same age, same magnetic profile, and yet they're still flaring at extreme levels. So, what's stopping our star from doing the same? No one's found a clear answer. And that's what makes this question so hard to ignore. The Parker Solar Probe and Solar Orbiter weren't designed specifically to look for superflares, but the data they're collecting might help us figure out whether the sun has that kind of energy stored up, especially now, during the solar maximum, when activity is at its peak. Some scientists believe superflares might start with the same kind of magnetic buildup we're seeing right now, regions of high sunspot activity, strong twisted magnetic fields, and sudden energy releases. If those fields get large enough and snap in just the right way, it could trigger something much bigger than a typical flare. Something we've never seen before. There's no direct evidence that the sun has produced a superflare in recorded history. The Carrington event in 1859 is the strongest known, but even that falls short of the flares we've seen from other stars. However, there are a few strange clues buried in ice cores and tree rings, sudden spikes in radiation that don't line up with anything else we know of. Some of them go back over 1,000 years. No one can say for sure what caused them. But the timing and the intensity suggest they could have been triggered by solar events far more powerful than anything we've seen in the satellite era. And here's where things get even more uncertain. We've only been monitoring solar activity in detail for a few decades. That's nothing in cosmic time. For all we know, superflares might be something the sun does once every few thousand years. We just haven't been around long enough to see one. So now we're stuck with a possibility that's not easy to dismiss. The sun might have a kind of energy threshold. It only crosses under specific conditions. Maybe it needs just the right magnetic buildup. Maybe it only happens when multiple regions of instability line up perfectly. Maybe what Parker just flew through, the merging CMEs, the magnetic folding, maybe that's the early version of it. Or maybe it's just a preview of what's possible. There's no countdown, no warning light, no way to know when or if it would happen. That's what makes it hard to talk about. There's no prediction, only preparation. But now, for the first time, we have the tools to actually see it coming, if it ever does. There was a time when studying the sun meant waiting. You'd spot a sunspot through a telescope, sketch it, wait a few days, and hope something interesting happened. Most of what we understood came from patterns, not live data. We knew the cycle, we saw the flares, but we were never in the room when things actually went off. That's changed, completely. With Parker flying through eruptions, Solar Orbiter catching the poles, Muse built to scan energy layers, and Punch imaging the solar wind, we've moved past observing the sun. We're now inside its environment, listening to it, tracking every twitch, and seeing events unfold as they happen. Not minutes later, not hours. Live. That might not sound like much, but it changes how everything works. Before, when a flare erupted, we'd only see its effects after it hit Earth or a satellite. Now, we can detect the eruption from the source and watch how it develops as it travels. That's not just valuable, it's critical. Especially because these events aren't always what they seem. A solar flare might look small at first, but if it triggers a chain reaction, like what Parker just saw, it could build into something stronger mid-flight. Without real-time tracking, we'd never catch that escalation. We'd be relying on outdated models to predict where it's going and how hard it'll hit. Now we're starting to build models based on actual footage, not assumptions. That's a huge leap. For the first time, scientists can test solar theories against live measurements from inside the storm. Every time Parker goes around the sun, it flies a bit closer, sees a bit more, and records how magnetic energy changes in ways we've never been able to measure. And what we're learning is that the sun isn't as simple as we thought. Its magnetic field doesn't follow clean loops. The solar wind doesn't flow evenly. Some flares build up and fade quietly, while others erupt suddenly without any obvious cause. We're starting to see turbulence, irregularity, signs that the deeper magnetic structure of the sun is less like a rotating bar magnet and more like a restless, tangled system of ropes under tension, snapping, reconnecting, and releasing energy without warning. And that leads to a bigger shift, not just in the data, but in how we talk about the sun itself. For decades, the sun was treated like a solved problem, not entirely, but close enough. We knew its structure, we knew its cycles, and we mostly thought it would keep doing what it's always done. But now that we're looking closer, we're seeing signs that some of those assumptions were too neat, too tidy. The real behavior is more complex, and maybe a little more dangerous than the story we've been telling ourselves. We're not just learning more about the sun, we're realizing how much we didn't know, and we're watching it change, adjust, react, and evolve. Not just over centuries, but right in front of us, while we're still here to see it. That's new. That's not something we've ever had before, and it means we're finally in a position to not just respond to solar events, but to understand them as they unfold, and maybe one day to predict them before they begin. The sun has always been there, every day. Same spot in the sky, same quiet warmth. It's so consistent that we almost forget it's a living object, changing, reacting, throwing off energy and light like a machine that never shuts down. But it's not a machine, it's a star. And like every star, it has layers we're only beginning to understand. For a long time, we looked at it like it was settled, under control, a system with patterns, rules, and boundaries. Now we're watching those boundaries bend, flares overlapping, magnetic fields collapsing into each other, quiet spots turning volatile, the kinds of things that don't show up in school textbooks because we hadn't seen them until now. This year, this solar maximum isn't just a statistical uptick. It's revealing a side of the sun that's messier, more dynamic, and more unpredictable than most scientists expected. And it's not a theory anymore. We have real footage, real readings, and real consequences playing out here on Earth. Parker flew through a storm that wasn't supposed to exist in that form. Solar Orbiter saw the poles twist in ways no one predicted. Punch is finding energy where there shouldn't be any. One by one, the old models are starting to crack. Not because they were wrong, but because they were incomplete, too clean, too confident. And if you think about it, that's not surprising. This is the star that made us. Every breath, every plant, every drop of water on Earth is tied to its light. But we've only just started looking at it properly, really looking, with the kind of tools and precision that weren't possible even 10 years ago. What we're learning now might change how we build satellites, how we protect astronauts, maybe even how we think about other stars in the galaxy. Because if the sun, our supposedly stable, medium-sized, ordinary star, can act like this, what else are we underestimating? For now, we keep watching. And maybe that's the most important part. We're not guessing anymore. We're not waiting for signals to reach us. We're out there, inside the storms, listening to the sun in its own language, and finally hearing what it's been trying to say.